In this section, we have three objectives. First, understand the concept of partial fraction decomposition. Second, use partial fraction decomposition with linear factors to integrate rational functions. Lastly, use partial fraction decomposition with quadratic factors to integrate rational functions. The method of partial fractions is a procedure for composing a rational function into simpler rational functions, to which you can apply the basic integration formulas. To see the benefit of the method of partial fractions, consider the integral below. Now, we try to evaluate this integral without partial fractions. So, we can use combine the square and use trigonometric substitution to obtain. Now, for this step, we use combine the square. So, we have x minus 5 over 2 square minus half square. So, it's variable minus constant. Recall back the trigo substitution in the section 4. So from here, u is equal to x minus 5 over 2. So this is a u, and u equal to half secant theta, and the a is half. And then we try to get the dx d theta. So dx d theta will equal to half secant theta tangent theta. And we perform the change of variable. So we have this form, and then we simplify, and we have to integrate the cosecant theta with respect to theta. And based on the basic integration rule, we have 2 natural log of cosecant theta minus cotangent theta. And based on the triangle, we obtain the cosecant theta and the cotangent theta. And we simplify our answer. And for this step, we use the natural log property, where the division can be converted to the minus. So this is the answer. Now, suppose you had observed that 1 over x squared minus 5x plus 6 is equal to 1 over x minus 3 minus 1 over x minus 2, where this step is partial fraction decomposition. then you could evaluate the integral easily as follows. Now, to integrate this 1 over x squared minus 5x plus 6 with respect to x without using the trigo substitution, where the 1 over x squared minus 5x plus 6 is equal to this simpler rational function, and we can easily integrate this integrand. We use the change of variable, and lastly we will get the same answer. This method is clearly preferable to trigonometric substitution. However, its use depends on the ability to factor the denominator x squared minus 5x plus 6 and to find the partial fraction 1 over x minus 3 and negative 1 over x minus 2. In the next slide, there will be the guideline for you to find the partial fraction. Recall from algebra that every polynomial with real coefficients can be factored into linear and irreducible quadratic factors. For example, the polynomial, this one is a fifth order polynomial. Then this polynomial can be written as x minus 1 times x plus 1 square times x squared plus 1, where we perform the synthetic division. For the first factor, x minus 1 is a linear factor. And for the second factor, x plus 2 square is a repeated linear factor. Look at the x plus 2. X plus 2 is linear. It's a linear function because the order of x is 1. So that's why it's a linear factor. But then why we call it repeated? Because there's a square. Meaning that x plus 2 times x plus 2. So for the square, we say repeated thrice. And x squared plus 1 is an irreducible quadratic factor. First, we say quadratic factor because of x squared plus 1 is a quadratic function. And why we call irreducible? Because x squared plus 1 cannot be factorized anymore to get the simpler form. Using this factorization, you can write the partial fraction decomposition of the rational expression. Nx over x power to the 5 plus x power to the 4 minus x minus 1, where the nx is a polynomial of degree less than 5 because it's proper fraction. If the nx is greater than or equal to 5, so we should perform the long division. And based on this rational function, nx over this polynomial, where in the previous slide we have factorized this polynomial. So we have x minus 1, x plus 1 square, and x squared plus 1. And then this rational function can be written into this partial fraction. Look at the partial fraction. For the first factor, it's a linear factor. So we write a over x minus 1. For the second factor, we call repeated linear factor. So we have b over x plus 1 plus, again, because it's repeated and the order is 2, so again c over x plus 1 square. And the last factor, x squared plus 1, is not repeated, so plus dx plus e over x squared plus 1. We have a guideline in the next slide. Look at the guideline of decomposition of rational function and x over dx into partial fraction. First, if we have improper fraction, so when our rational function is an improper fraction, that is, the degree of the numerator is greater than or equal to the degree of the denominator, so divide the denominator into the numerator to obtain this form, where the degree of n1x is less than the degree of dx. So this rational function is a proper fraction. Then we can proceed to second, third, and the last step, to the proper rational expression. Okay, for the second step, factor denominator. Completely factor the denominator into factors of the form px plus q power to the m and is ax squared plus bx plus c power to the n, where ax squared plus bx plus c is irreducible, meaning that the ax squared plus bx plus c, this quadratic expression, cannot be factorized anymore. For linear factors, for each factor of the form px plus q power to the m, the partial fraction decomposition must include the following sum of m fractions. For example, if the m, the order here is 2, is square, so the partial fraction is a1 over px plus q plus a2 over px plus q square. Stop. Because we know when we have a square here, we call a repeated linear factor. And if the m here is cubed, for example, the m here is cubed, so our partial fraction must be a1 over px plus q plus a2 over px plus q square plus a3 px plus q cubed. Stop. Now for the last quadratic factors. For each factor of the form ax squared plus bx plus c power to the n, the partial fraction decomposition must include the following sum of n fractions. If the n is just only 1, so it's not the repeated, so the partial fraction is b1x plus c1 over ax squared plus bx plus c. If the n is square, so is repeated quadratic factor. So we will have the partial fraction b1x plus c1 over ax squared plus bx plus c plus b2x plus c2 ax squared plus bx plus c squared. Stop. Look at this example. Write the partial fraction decomposition for 1 over x squared minus 5x plus 6. Because we know that the x squared minus 5x plus 6 can be factorized, so we have x minus 3 times x minus 2. You should include one partial fraction for each factor and write 1 over x squared minus 5x plus 6 equal to a over x minus 3 plus b over x minus 2. So look at this statement is for each factor. So for this quadratic expression, we have two factors, which is x minus 3 and x minus 2. So for the first factor, it's a linear factor. So for the linear factor, you refer to the previous page, the guideline, the third step. So we write the partial fraction. We have a over x minus 3. Because the order here is just only 1, so stop. Then for the second linear factor, also is a linear factor. The order is still 1, so we have plus b over x minus 2, stop. Where a and b are to be determined. Multiplying this equation by the least common denominator, x minus 3, x minus 2, and produce the basic equation. Meaning that we multiply this equation by x minus 3, x minus 2. Okay, both sides. Where for the left side, we can easily simplify them. So it's 1, no more. So it's 1 over 1 is 1. But for the right side, this term, we expand, or we say multiply by x minus 3, x minus 2. But the x minus 3 can be cancelled. So a will multiply by x minus 2. So which is, okay, we obtain here. Then plus this term multiplied by x minus 3, x minus 2. So the x minus 2 can be cancelled, can be simplified. So b times x minus 3. So this equation we call basic equation. Because this equation is to be true for all x, you can substitute any convenient value for x to obtain equation in A and B. The most convenient values are the ones that make particular factor equal to 0. And we know that we have two linear factors. The first factor is x minus 3. So we let this factor equal to 0. We have x equal to 3. Meaning that we substitute the x equal to 3 into this factor, we will get 0. So to solve for A, let x equal to 3. So we substitute the x into the basic equation. So look at this factor. We will get 0. Then in one equation, one unknown only, because 0 times b is 0. Then we can solve for A. Look at this step. To solve for B, let x equal to 2, and we obtain. So look at this step. We let x equal to 2, you can see this factor equal to 0. So we can solve for B. Because in one equation, we just have only one unknown. We can solve for B, so B is negative 1. So we can substitute our A and the B value into our partial fraction. So that is why 1 over x squared minus 5x plus c can be written as 1 over x minus 3 minus 1 over x minus 2. You actually can try to group these two rational functions into one rational function. You will get the rational function that's same as the left side rational function. You can try to prove. Look at this example. Let's say we have this question. Look at the denominator, where for the first factor still can be factorized. For the x squared minus x, we can factorize up the x. So we have x into x minus 1. And then for the x squared plus 4, this is an irreducible quadratic factor. So total, we have 3 factors. Total, we have 3 factors. So the first factor is linear factor. And the second also is a linear factor. and the third factor is a quadratic factor. But none of them is repeated factor because the order is just only 1. So you should include one partial fraction for each factor. And right, for the first factor is a linear factor, is a over x stop. And the second factor, x minus 1. So b over x minus 1 plus the last factor is a quadratic factor, so refer to the step 4. We should have two unknowns. So we write cx plus d over x squared plus 4, then stop. Okay, so now the next step, same as the previous example. The whole equation multiplied by x minus 1, x squared plus 4. The whole equation multiplied by this. Then we produce the basic equation. So where the left side we can just simplify them. So we just have 2x cubed minus 4x minus 8. And the right side, for the first term, the x and the x here can be simplified. So the a will be multiplied by x minus 1 and x squared plus 4. But for the b, the second term, if we multiply by this whole thing, the x minus 1 can be cancelled. So the b will multiply by x and x squared plus 4. Here, x and x squared plus 4. And the third term, the x squared plus 4 can be cancelled. So the cx plus d will be multiplied by x and x minus 1. So we simplify. Then to solve for a, we let x equal to 0 because the first factor is just only the x. The first factor is x, so let the first factor equal to 0, so x is equal to 0. So we substitute the x equal to 0 into the basic equation. Then we can solve for a. And for the second factor is x minus 1. So we let x equal to 1. So this factor will be equal to 0. We let x equal to 1. So we substitute the x equal to 1 into the basic equation. Then we can solve for b. And for the third factor, we know that our third factor is x squared plus 4. This is our third factor. But then this factor, when we substitute any value of x into this quadratic expression, we will not get 0. This is impossible to let this factor equal to 0. Impossible. So, at this point, c and d are yet to be determined. You can find this remaining constant by choosing two other values for x. And solving the resulting system of linear equation. Since we have let x equal to 0 and x equal to 1 to get the a and b values, for the other two values, we can let x equal to -1. Just any value as a small value because easier to calculate. So we substitute x equal to -1, and what we have obtained, a equal to 2 and b equal to -2 into basic equation. And we simplify, we have this equation involving the c and d unknowns. For another value, we can let x equal to 2, just any value. Then we substitute the 2 into the x, okay, in the base equation, and the a equal to 2 and the b equal to -2 as well. And then we simplify, and we obtain this equation. We can let this equation as the first equation, and this equation as the second equation. Then we solve them by simultaneously. It's either we use substitution method or elimination method. After we get the c value, we can substitute the c value into any equation to get the d value. After we obtain the d value, we can substitute the a, b, c, d values into partial fraction. Perform the integration on right side easily, where they are in the sum or different form. We can straight away to integrate them. So for the first term, we integrate 2 over x with respect to x. So where the 2 is a constant, so we integrate the 1 over x. So we factorize out the 2, so we just integrate the 1 over x. So where we integrate the 1 over x is natural log of x. And for the second term, also the same. Let u equal to x minus 1. So we perform the change of variable. So du dx equal to 1. So we have 2 over u, where we integrate the 2 over u, 2 is a constant. So we can take out the 2, and we integrate the 1 over u is natural log of u. And for the third term, we can use change of variable method, where we can let the u equal to x squared plus 4, u prime equal to 2x. So this 2x is the derivative of the inner function, so it's a change of variable. And the last term, we cannot use change of variable, so we can use the inverse trigo formula. Here are some guidelines for solving the basic equation that is obtained in the partial fraction decomposition. For the linear factors, substitute the roots of the distinct linear factors in the basic equation. For repeated linear factors, use the coefficients determined in the first guideline to rewrite the basic equation. Then substitute other convenient values of x, and solve for the remaining coefficients. For the quadratic factors, expand the basic equation, collect terms according to powers of x, equate the coefficients of like powers to obtain a system of linear equations involving a, b, c, and so on. Lastly, solve the system of linear equations.